this whole site, which is now called the New Museums site, was originally, and in the Middle Ages, a monastery. It was an Augustinian monastery, right in the middle of town. And on the north side there was a series of monastic houses, a bathhouse, which is now a pub called the Bathhouse. And on the western side there was a stream running down into the Cam, which was basically an open sewer. That's now Free School Lane. When the university took over the monastery, it set up its first botanical garden here. And every early modern institution of learning, especially if it had medical students, had to have a botanic garden because those produced the herbs for medics. So this was where the university botanic garden was. And then in the early 19th century, the Botanic Garden, under its absolutely charismatic director, John Stephen Henslow, who was Charles Darwin's first patron, moved the Botanic Garden from its very constrained space here to the south of town, to the new town, as it was called, and it's still there. And the space that was left was then developed by the university in its first major building program for the sciences, which were a series of museums. And that's important, I think, for us to remember that in the 19th century, the chief institutions of science were not labs, but museums. Even sciences we don't normally think of as being pursued in museums were museological sciences, like engineering. When engineering started to be taught in Cambridge, it was taught from a museum collection. There was a museum of mechanism. So you would have tables and tables and then shelves and shelves of model machines. Model steam engines, model cranes, model pile drivers, model gears, and so on. And you learnt engineering at college by studying models of the machinery of the Industrial Revolution. And the first professors of mechanism, which is what they were called, taught from these museological collections. The same was true, obviously, of natural history and botany, of chemistry and so on. So the New Museums site speaks to the way in which this was the first scientific site in Cambridge. This is really all that's left of it, of that early to mid-19th century project, and it's now a series of examination halls. Everything else has been swept away. So that when the Cavendish was built at the end of the 1860s through the middle of the 1870s, it was built radically within a set of museums. Right? It was a big new lab which had to sort of interpolate itself in a model of university science which was essentially museological, which was essentially oriented around models. And that was part of the challenge that the Cavendish had to overcome. So we're at the entrance of the old Cavendish building in the middle of Cambridge, and I guess one of the ways of thinking about this extraordinary site is it's kind of an onion. There are layers and layers of history and science superimposed on each other here. It's a sort of archaeological site. It's one of a very few number of extraordinarily rich scientific sites in the world. I mean, this is a spectacular place historically and scientifically. And we should start really by looking at this. This looks, to the untutored eye, and maybe even the tutored eye, like a medieval structure. Here are the pointed arches, the cobblestones, the beautifully engraved wooden gates with verses from the Psalms on them, and opposite what is in fact a genuinely medieval structure, which is this clunch wall facing us, which is the eastern wall of Corpus Christi Hall. So the first thing that strikes you is this doesn't look like a modern building. This doesn't look like one of the sites where the modern world was invented, but it is. So we learn from this that in order for an extraordinary institution like a physics laboratory in the 1860s and 70s to be inserted into the clerical university, it was necessary to surround it with the appearance of tradition. So you learn something from this kind of architecture, that when experimental physics enters Cambridge University in the 1860s and 70s, it's cutting-edge, high-tech science, but it looks like a medieval system. And that was deliberate. The first professor of experimental physics in Cambridge, James Clerk Maxwell, brilliant Scottish mathematician, expert in optics and electromagnetism, was very conscious when he was designing this building of the danger that the more traditional dons would sense in having such a challenging, difficult, modern institution. So the medieval layout with its porter's gatehouse, its gates and its cobbles, its pointed arches, is quite deliberate. And Maxwell says in one of his letters in the early 1870s that if he was too successful, then the parents of the students would be around his ears complaining that instead of studying mathematics, they were being made to work in a laboratory. And that would be a disaster. And why would it be a disaster? Because it was a challenge to a class idea, a social idea of what an intellectual in Cambridge should do. An intellectual in Cambridge does pure mathematics and takes the mathematics tripos, which is a very competitive exam, and passes with flying colours and becomes a wrangler and does not work with his hands. Whereas what Maxwell and his allies were proposing here was practical engagement with experiments, with equipment, with instruments, and with the real phenomena of the world, and that seemed extremely challenging. So one's got to sort of think back to a world in which this is not tradition, this is radical modernity. There are other aspects of the design of the new lab which are very, very striking. If you look at the north wing, which is part of the original building, you notice, I hope, at least three things. One is, by 19th century standards, it's extremely big. This is a very large new building for a Victorian university. It can carry 3 workspaces on 3 floors, plus the support staff and infrastructure, which was normally in the basement. Secondly, you see how large the windows are. The windows are deliberately large because Maxwell was proposing a series of experimental investigations which needed very steady, bright illumination. So he goes back, interestingly, he and his architect, to a kind of Georgian vision of what the facade should look like. Much bigger windows than would have been traditional at the time. And then the platforms in front of the windows are not, as you might imagine, for flower boxes, but for helioscopes, for mirrors which are driven by clocks which follow the path of the sun. So that's the southern sky, right? So the sun moves during the day when there is sun from that side to this. So you could bring sunlight into the lab and experiment on it. So it's an absolutely genial way of using solar light, in this case, to do experiments with spectroscopes, with prisms and lenses and so on. Okay, so it's this part and this part which is the Maxwell period. At that stage, what the Cavendish is doing in terms of research is almost entirely around the problems of electricity and magnetism, the cutting-edge technology of the time, but analysed in terms of Maxwell's new theory of electromagnetism, which he publishes in the early 1870s, the Treatise on Electricity and Magnetism, which is the classical, as we would now say, statement of the claim that electromagnetic waves are waves in an ether, a fluid which fills all space, and light is a form of electromagnetic radiation. Revolutionary idea that one generation later will lead quite directly to Einstein's development of the special theory of relativity in 1905. So this is modern physics. The most important challenge for Maxwellian physics was measurement. It was necessary to turn this lab into a measurement institution. And in order to make precision measurements on light, electromagnetism, and so on, it was necessary to network, to link this building in a small market town in the East Midlands with the global networks of instrument making, commerce, trade, and industry. So although it looks cloistered, in fact, this is a global institution. This is a centre of calculation. And it's closely linked to manufacturers in Liverpool and in Germany, in Paris and in London, who supply the hardware, the skills, the techniques, and many of the workmen who make the lab tick. And by the time of Maxwell's tragically early death in 1879, the Cavendish had become a standards institution for the world, in which the value of the unit of electrical resistance, the ohm, was set here, in these buildings, by Maxwell, by his students, and by his brilliant but extremely eccentric successor, Lord Rayleigh. Rayleigh was the second professor here, an aristocrat, Baron Rayleigh, John Strutt, who mainly earned his living from a series of family farms in Essex, which grew dairy cattle. And when I was growing up in London, you still got milk delivered in vans with Lord Rayleigh's Dairies written on the side, right? And in a marvellous letter, when Rayleigh is discussing whether or not he's going to take the job in succession to Maxwell, who was a very close personal friend, Rayleigh says, well, I'll take the job for a few years until the agricultural depression is over, and then I'll go back to the estate. The estate is at Tarling, down in Essex, beautiful house with its own private lab, and Rayleigh partly treated the Cavendish as a kind of extension of his private inquiries. He completed the measurement of the ohm, the electrical resistance work. He hired new, clever laboratory demonstrators. He massively expanded student numbers. He instituted a completely new, revolutionary really, system of laboratory training, in which next to every desk in the classrooms inside was a manuscript book with a description of the experiment next to it. And the student was expected to read the instructions, perform the experiments, write the results, and then move on to the next experiment. So you had the invention of that standard Cavendish model of how you train intellectuals to use their hands, which is by reading and then experimenting. There are magnificent anecdotes from people who went through the system about how cack-handed they were. They couldn't use a Wheatstone bridge. They always made batteries blow up and so on. And I think there is where a certain kind of myth about Cambridge physics, Cambridge science in general really, comes from, which is the myth of sealing wax and string, as it's called. In other words, the myth that these are amateur gentlemen with not many commercial interests who use cheap, improvised apparatus to discover the secrets of the world. The only bit of that story that's true is the last sentence. They did unlock the secrets of the world, but they are industrialists. They are extremely well networked to global electromagnetic power and light systems, and a lot of the equipment is very expensive and highly precise and doesn't just rely on sealing wax and string. But the way in which the students were taught tended to cultivate the idea of the ingenious amateur improviser. It's the sort of grandfather figure of the boffin who will appear as Q in James Bond. No hair, long white coat, does things cheaply, they work, unlike the gee-whiz science of the Americans and the Germans. That's not, I think, historically accurate. It's very important politically. When the agricultural depression ended, Rayleigh went back to his farms and then eventually to take over the big new lab at the Royal Institution in London, where in the 1890s he and his colleagues, William Ramsay especially, were the first to identify the noble gases, argon, neon, especially argon in the 1890s. Rayleigh was succeeded by an extraordinary man, a bright, young, Manchester-trained mathematician who was, at that point, absolutely hopeless at experimental science, and his name was J.J. Thomson. And he's my favourite physicist of all time. J.J., he was always known to his friends and students. He ran the lab from 1884 until 1919, which is one of its great periods. And initially, He maintained the commitment to precision measurement, to electromagnetic standards, and so on. But part of JJ's genius is to be able to spot where the action is, where the exciting new developments are happening. And JJ's particular interest was in a phenomenon called cathode rays. So when you heat a metal plate inside an almost completely evacuated glass tube, you begin to notice, especially if it's slightly dark, incandescent rays filling the tube, right? And because they seem to come from the negative plate, they're called cathode rays. And this is the great-grandfather of television. The problem was, what are these rays? JJ began to be convinced that these glowing rays are particular. They're something like charged particles. Most scientists, especially in the German lands, thought the opposite. They thought that cathode rays were rays. They were a form of wave. So in the 1890s, JJ and his collaborators began to analyze what these rays really are to try to show that they're particular in quality. And he was immensely aided by the fact that at the end of 1895, beginning of 1896, a German scientist called Wilhelm Röntgen, began to produce a new form of electromagnetic radiation, which we now call X-rays, which were then called Röntgen rays. And what JJ and his students here immediately spotted is that if you fire X-rays through a cathode ray tube, it gets extremely highly charged. And then if you pass a current through the tube, the charge collapses. So using that technology and applying magnetic plates, so a strong magnetic field on either side of these tubes, it was possible to move the ray's position. You could shift it. And that immediately confirmed, as far as JJ was concerned, that these things are particles. They are not waves. They respond both to electric and magnetic forces. You can make them shift. It's the principle of the television, exactly. And by 1897, he was able to say that what's in cathode rays are tiny, tiny, negatively charged particles, which we now call electrons. Now that work is done here, in this part of Cambridge, which was built in the 1890s and then through down there to about 1910. And again, the legend is that these experiments are cheap and cheerful, they rely on sealing wax and string, they're highly improvised. This is nonsense. In order to make these extraordinarily elegant sausage-shaped pieces of glass, you need to be a great glass blower. Because what you're doing is, I mean, one of these tubes is about yay big, and it has 6 or 7 junctions where you have to bleed metal wires through the glass, right? Yet so carefully that no air can come in or out. So that blowing the glass and then leaving these holes so that you can then bleed metal wires through the glass with little metal plates on them, this is incredibly high tech. So what you see emerging in this building along here in the 1890s through to the outbreak of the First World War is a community of fantastically sophisticated technicians. W.G. Pye, William Garnett, people like this, who were the lab technicians. And they are the unsung heroes of the Cavendish tradition, really. Without them, there is no Cavendish physics. And they don't win Nobel Prizes, but without them, you don't make discoveries. Okay, that's straight. Right. The next great event, I suppose, to focus on, and now we're sort of here, roughly, in terms of history, is, as usual in Cambridge University, there's always a close relationship between its scientific triumphs and administrative changes, which are always slightly out of sync. Right? That's, I think, still true, but let's not dwell on that. In 1895, there was a change in the regulations of the university which had dramatic consequences. It seems trivial, it was actually very important. It was, for the first time, it was possible for someone who didn't have an undergraduate degree from Cambridge to do a research degree here. And that was amazingly important because for JJ, it meant that he could start to recruit scientists from elsewhere. to do doctorates with him in the doctoral students' labs in this building. And in '95, two really important physicists arrived to work with JJ. One is C.T.R. Wilson, who had previously been working rather uncomfortably on top of Ben Nevis in the Scottish Meteorological Office's observatory there. No doubt the most uncomfortable scientific lab in the world, right? And the reason he was there was because he was interested in clouds. He was obsessed by how clouds form, how vapor condenses, and the mechanism by which that's done. And his intuition was that vapor, water vapor, condenses especially on tiny charged particles. So rather than spend the rest of his career commuting between Fort William and the top of Ben Nevis, he moves to Cambridge and begins to design a series of machines which are called cloud chambers. Cloud chambers are tiny, initially cylinders about so big, with a pump underneath and a receptacle for purified water and a glass lid so you can see what's going on in the chamber. You quickly take all the air out of this tiny chamber, and the water vapor from the reservoir will then form droplets inside the chamber. If there's any charged particles in that chamber, the water droplets will form at those particles. Now, from Wilson's point of view, this was a demonstration of his theory of how clouds form. But from JJ's point of view, as usual, he saw everything the other way round. He realized this was a way of seeing tiny charged particles, because there will be a water droplet wherever there is a charged particle. And if you have a strobe light or a flashlight attached to a camera, you can take a picture, and you've actually photographed a cloud of charged particles, electrons, or other kinds of charged particles. So cloud chambers are ways of seeing subatomic particles. And that was an extraordinarily revolutionary technique, and it was developed here. The other great arrival of 1895 is an eccentric, rather aggressive, tough-minded New Zealander called Ernest Rutherford, who wasn't, when he got to Cambridge, terribly impressed, it must be said. He thought JJ was a fossil. That's what he writes to his girlfriend back in New Zealand. He was much more impressed, interestingly for us, by the extremely smart middle-aged anthropology lecturer, Haddon. Rutherford and Haddon used to cycle out to Cambridge villages as part of the folklore survey that the British anthropologists were engaged in the mid-90s. Rutherford describes cycling out to Barrington, which is a village about 8 miles south of Cambridge, with Haddon on his bike and interviewing all the villagers and then cycling back. So you have this wonderful moment when this New Zealander from Aotearoa accompanies Alfred Haddon to do an anthropological survey of Cambridge villages. It's sort of wonderful inversion. So when he wasn't doing that and writing rather sickeningly affectionate letters to his girlfriend, he was working on the most important, interesting new technology at the time, which was radio. Rutherford was responsible already, I mean, he's only in his 20s, right? He was responsible for the first radio propagation in Britain, certainly in Cambridge. He set up a radio transmitter on top of the tower of St John's College Chapel and walked backwards along Portugal Street and then backwards across Jesus Green, carrying a spark gap, so that when the radio waves hit the spark gap, you would get a sudden spark there. And he was able to see that this was a form of electromagnetic radiation that could travel a long way. He proposed this as a PhD topic to JJ, and JJ said, no, forget it, it's useless. Instead, Rutherford was turned by JJ very much towards work on the much more exciting new phenomena of the mid-1890s, X-radiation and radioactivity. What Rutherford then does is to leave Cambridge in '98 for a prestigious new job in McGill in Montreal, which was one of the largest physics labs in the world. One should remember this. It was entirely funded by a Montreal tobacco magnate who was a fierce anti-smoker, very interesting man, who made so much money out of cigarettes that he was able to build for the university in McGill this ridiculously well-funded physics lab. And there in Montreal at McGill, and then from 1906 onwards at Manchester, the best physics lab in Britain at the time, Rutherford and his collaborators, Soddy in Canada and Geiger and Marsden in Manchester, laid the foundations of modern radioactive science. What Rutherford and his colleagues showed was that when radioactive salts like radium or polonium decay, they give out three kinds of radiation: alpha, beta, and gamma. Those were the names that Rutherford coined. Alphas, he established, were the nuclei of helium. Betas were the same as J.J. Thomson's tiny negatively charged corpuscles, electrons. And gamma was a form of electromagnetic radiation, rather like X-rays. So those are the three products of radioactive decay. And Rutherford became a kind of master naturalist of these phenomena. His two great Manchester projects were, on the one hand, between 1909 and 1911, working with Geiger and with Marsden, they would use alpha particles, so what we now think of as helium nuclei, to fire them at very thin pieces of gold leaf, and then see how they were scattered. And the scattering pattern, which was astonishing, revealed that gold atoms must consist of a really tiny nucleus, as they called it, and then a vast, almost entirely empty cloud, mainly negatively charged. Right? So a tiny nucleus which has a strong positive charge, and then a cloud of negative charge around it. One image that was used at the time is the fly in the cathedral. The nucleus is the fly and the atom is the cathedral. That's roughly the ratio of size of nucleus to the whole of the atom. But Rutherford puts it more beautifully, I think much more beautifully than that. He says, if you fire alpha particles at gold leaf and you find them being pushed back towards you with a huge scattering angle, it's exactly like firing a naval shell at a piece of tissue paper and finding it bounce back. It was so astonishing. And his other great breakthrough, apart from establishing the basic geometry of the nuclear atom, the planetary atom, was just at the end of the First World War, 1918-1919, when he fired alphas at nitrogen and found that he was getting hydrogen as a product. This is the first artificially produced nuclear disintegration. An immensely important experiment. That was all done in Manchester. During the First World War, a lot of Rutherford's Manchester team was broken up. Some of them were killed during the war. Some of them were captured and held as prisoners of war. Rutherford himself was mobilized to work on submarine detection at a naval base called Hawke Craig, where he did the first important work on sonar. And I think there's a really interesting connection, hasn't really been explored properly, between Rutherford's interest in using sound waves, sonar, to detect otherwise invisible objects like submarines deep beneath the sea, and his fascination with particle detection. Right? There's clearly a transfer of technique and method between the two projects. They aren't separate, and they inform each other. And in 1919, great event in the history of Cambridge science, J.J. Thomson retired from running the Cavendish, became head of Trinity College, and he was replaced by Rutherford. It was an absolutely uncontested appointment. Rutherford was the leading particle scientist in the world, bar none, and for the next 18 years, he ran this institution. So now we're talking about really a very big plan extending all the way down to beyond the spiral staircase there, and with other buildings too. He recruited globally from across Europe, North America, and the Commonwealth. One of his most brilliant and eccentric recruits and allies was the great Russian scientist Peter Kapitsa. Kapitsa was a genius, eccentric, hilarious, very jokey, much more interested in theoretical science than was Rutherford. A communist, absolutely convinced Soviet communist, mainly interested in low temperature physics and the behavior of magnetism. So he did Rutherford and Kapitsa, a lot of money from ICI, from Ludwig Mond, big chemical manufacturer, to build this building here, which is in fact my favourite building in Cambridge because it's the first modern laboratory. I mean, we started with a quasi-medieval, cobbled, overwrought Gothic piece of pointed arch, and by the 1930s you have something like this. So this was the Mond Lab, run by Kapitsa, and it's a beautiful piece of Bauhaus architecture, which I adore. And on the wall, this is what you have to attend to, is a crocodile, which was designed by Eric Gill, the great modernist artist and designer. And the crocodile stands for Rutherford, because crocodile, was Kapitsa's name for his boss. And there are various stories about why, right? One story is because once Rutherford grasped something, he never let it go. One story is because if you criticized him, he bit your head off. One is because actually crocodiles can't turn their heads, so they're kind of oriented towards a single line of inquiry. Whatever the reason, that's Rutherford, according to Kapitsa. It's not quite recorded what Rutherford thought of having a cartoon by Eric Gill actually built into the brick of this expensive new part of the laboratory. What was Rutherford's main project at Cavendish? It's very much centred in this tower. Coming here from Manchester, Rutherford was already in command of the basic principles of nuclear physics. So he knew that atoms are made up of arrays of negatively charged electrons orbiting around a strongly positively charged nucleus, and that the number of charges in the nucleus must be the same as the number of negative charges orbiting around it, because atoms are electrically neutral. And those numbers, which are called atomic numbers, characterize the chemical properties of atoms, of elements, which the atoms make up. It was Niels Bohr, the great Danish physicist, who visited Manchester just before the First World War, who developed this brilliant model of the planetary atom and of an explanation of how radiation can be emitted and absorbed by atoms through electrons jumping from one orbit to another by using the principles of what we now call the old quantum theory. So a strong alliance, I think, in Rutherford's project between theory and experiment. This is the second legend that I think is completely false. If the first legend is they made it up as they went along, all the equipment was cheap, it was sealing wax and string, they were amateurs, that's nonsense. The other nonsense is Cambridge physics in general and Cavendish physics in particular is typically associated with what you might call theoretical philistinism. Right? So Rutherford is often quoted as saying, I don't know what these particles are really, but to me they seem like jolly little beggars, rather like billiard balls, coloured red or green depending on taste. Right? It's true that Rutherford, with a strong New Zealand accent, which I will not attempt to imitate, said things like that. But in fact, there's a very, very sophisticated theoretical project going on in the lab at exactly the same time as the experimental work. Very high-class theoreticians, like Bohr in Manchester, or above all, I think, George Gamow here in Cambridge, really inform the experimental projects. And the experimental projects are absolutely designed to challenge, revise, correct, or amplify theoretical models of what's happening in the nucleus and in the atom. A very good example of this is Rutherford's great Bakerian lecture of 1920, in which he argues that it must be the case that the nucleus is not only made up of small positively charged particles, what we call protons, hydrogen nuclei. There must be something else, and these particles would be electrically neutral, and they're called neutrons. For a decade, Rutherford tried to accumulate theoretical and financial support for this theory. Right? Gamow comes to Cambridge to work with them. He recruits James Chadwick, who'd been a prisoner of war in Berlin during the First World War, and Chadwick directs a research program on this problem. It's not until the late 20s, early 30s, that the problem begins to become experimentally tractable. And it becomes experimentally tractable, again I emphasize this point, because of the fantastically close links that Rutherford had with industry, because of his Manchester days. Right? He was very, very closely associated with a big manufacturing concern, Metropolitan Vickers, who supported the lab with enormous amounts of money and hardware and electromagnetic equipment. Without that, the great achievements of 1932, which I'm going to talk about now, would just be unthinkable. So in 1932, the golden year of Cavendish physics begins when Chadwick, trying to copy some experiments initially done by the Joliot-Curie team in Paris, fired alpha particles, slow helium nuclei, at beryllium. And whatever the product of that collision was, it seemed to be extraordinarily penetrating. And the alliance between theory, high-tech, and experimental genius here in early 32 suggested at once what this very penetrating radiation must be. If it's very penetrating, that's to say it's not stopped by electric charges, that must mean it doesn't have an electric charge. And these are neutrons. This is Nobel Prize winning work. This is no doubt one of the most important experiments of the 20th century, because these are the experiments that not only produce evidence that there are neutrons in the nuclei, but begin to suggest how you can control them. And we know, tragically, what that will lead to within 10 years, the construction of nuclear fission and chain reactions and the production of large numbers of neutrons, because since neutrons are neutral, they can move into the nucleus and divide it and generate more neutrons. This will be the achievement of Enrico Fermi in Italy and then in the United States, and then large numbers of physicists, both in the German lands and in North America and Britain, during the later 30s and then during the war at Los Alamos. At exactly the same time, again supported by Metropolitan Vickers Limited, Cockcroft and Walton began to design stronger and stronger electromagnetic accelerating machines, which would allow very fast particles to be fired at nuclei and potentially to split them. And towards the end of 1932, Cockcroft and Walton firing very fast, very accelerated protons, small positively charged particles of lithium nuclei, divide the lithium, split it into alphas, into helium nuclei. The first controlled artificial disintegration. So by 31, 32, this is all Nobel Prize winning work, Rutherford's program is really delivered. And he persuaded his mate, Arthur Eddington, who was astronomy professor at the time and another of my heroes, to write a kind of fundraising pamphlet for the lab on the basis of these triumphs, because the lab was always short of money, because it was a high technology institution. And it was Eddington who coined the phrase annus mirabilis to describe what had happened in 1932, these great discoveries of neutrons, of artificial disintegration, and indeed the first production of the positron, the anti-electron. In several ways, one might say that represents the culmination of Cavendish physics or nuclear physics, right? These guys were masters of an incredibly complicated set of techniques, and they'd reached, I think, to a certain extent, the limits of their resources. What we now know in retrospect is that this building had, as it were, reached the limit of what you could do without a further, to coin a phrase, quantum leap in funding, technology, and scale. The future of nuclear physics was industrial, and that just wasn't feasible on a site like this. Rutherford died again rather young and tragically in 1937, and was replaced by Lawrence Bragg. Bragg was born in Australia, in Adelaide, counted himself British, and he was an expert, above all, on how to use X-rays to study the structure of crystals and of nuclei. Bragg arrived as head of the Cavendish Lab in the late 1930s, in 1937, and rather like J.J. Thomson and very much unlike Rutherford, Bragg's genius, I think, as laboratory director, was to spot who amongst his young associates was asking the most interesting questions and what new kinds of science the lab should encourage. And the two great achievements, really, of Bragg's period are utterly surprising for what had been, for 70 years, the world's leading physics lab. On the one hand, Bragg understood extremely well how the techniques of X-ray crystallography could be used much more widely. So X-ray crystallography is, in principle, simple, and in fact, immensely complicated. It is based on the principle that electromagnetic radiation of very high frequency, so very low wavelength, will be scattered and diffracted by structures whose spacing, whose orderly spacing, is comparable with the tiny wavelengths of that radiation. That means crystals. So you could treat a crystal as a kind of diffraction grating, and you could determine the structure of a crystal by observing and capturing, photographically typically, the diffraction patterns when you fired X-rays at them. The master of this technique was a man whom Bragg and Rutherford both loathed. He was called J.D. Bernal. He was a communist, visionary, socialist activist, anti-war campaigner, founder of the Cambridge Scientists' Anti-War Group during the Spanish Civil War. He helped organize a model of a Basque village to be built on King's Parade and then blew it up to show Cambridge dons what the effects of fascist attacks in the Spanish Civil War were. Bernal was also a womanizer, a hedonist, interested in art and architecture, a friend of Gropius and Moholy-Nagy, utterly unlike the, it must be confessed, extremely Philistine Rutherford and the slightly genteel, though Australian, Bragg. When Bragg became head of the Cavendish, Bernal left Cambridge for London and became head of the crystallography lab down at Birkbeck. This left exactly one person in the whole of the Cavendish who was nearly as good at using these techniques to look at biological crystals, and his name was Max Perutz. He was a refugee from what had become fascist Austria. Rutherford and then Bragg were instrumental in trying to get scientists out of Nazi Europe to safety in Britain and North America. It's one of their greatest achievements, and Perutz was exactly such a refugee. And Perutz was an extraordinary man. He was single-minded to an amazing degree, and he realized just before the beginning of World War II, so 1937 through to 1939 and then beyond, that you could use X-ray crystallographic, X-ray diffraction techniques to describe the structure of the vast organic molecules that control the processes of life, proteins, hemoglobin, and so on. During the war and just after 45 to 47, the group that Perutz was running consisted of exactly two people, Perutz and the amazing and very bright young John Kendrew. That was it. And Bragg, and it's an astonishing fact, instantly recognized that this is the future. And he did what Cambridge dons do when they want money. He went to dine at the Athenaeum and had lunch with the head of the Medical Research Council and managed to get just enough money out of the MRC to set up a unit within the Cavendish to use the X-ray techniques to describe the vast organic molecules on which life processes depend. And that rapidly expanded through the late 40s and into the early 50s, from 2 to about 45. In the early 50s, it recruits Francis Crick and then the young American Jim Watson. And in 1953, very much with Bragg's blessing and with Perut's and Kendrew's encouragement, these two young men, using both the kind of molecular biological techniques developed here, but above all, as we now know, using the X-ray photos of DNA, deoxyribonucleic acid, which had been made not here, but in London, at King's College London, by Maurice Wilkins and Rosalind Franklin, who were disciples of Bernal. They construct a molecular description of DNA, the famous double helix model. The myths about this story are all very well known, mainly thanks to Jim Watson's book, The Double Helix, which came out in the early 60s, and perhaps we shouldn't dwell on them here. But what is so striking is that this, the greatest discovery in biology of the 20th century, emerges from a physics lab and is incomprehensible without the very long tradition of practical engagement, model building, photography, manipulation of high energy radiation, which is characteristic of this institution, right? And thence molecular biology. A similar story can be told about the basement here. Our final story. In a very similar way, Bragg quickly recognized the immense scientific advances and significance of the work that had been done in the Second World War around radar, the telecommunications establishments, which had helped win the war for Britain. And radio engineers, especially those working around radar, notably J.A. Ratcliffe and his assistant Martin Ryle, had used radar technology and radio detection technologies to begin to explore radio waves arriving on Earth, at Earth, from deep space. So in the 1940s, again, I don't think this involved dinner at the Athenaeum, but it involved something very similar. Bragg managed to raise just enough money to set up what is essentially the first British radio observatory here. And during the 50s and 60s, again, not at all ceiling wax and string, but very sophisticated, very high-tech, precision engineering, radio detection. Ryle and his colleagues, Ratcliffe and his colleagues, begin to link together theoretical models of the universe and star formation with radio detection. One of the more interesting questions that they were looking at was what are called quasi-stellar objects, quasars, as we now call them. And the problem was that it was proposed by theory, by cosmological theory, that there must be tiny objects in deep space which seem to behave like stars but are much smaller than stars. So they're generating the amount of electromagnetic radiation, so the amount of energy that a whole sun generates, but they must be much smaller. And Hewish worked out a possible way of spotting these in terms of radio detection, radio astronomy detection, which is essentially looking for the ones that twinkle a lot. Right? It's a wonderful idea. So scintillation. Right? In the optical wavelengths, we see stars twinkling, and we see them twinkling because the light that reaches us from the stars has to pass through the Earth's atmosphere. So call that scintillation. Right? In the radio part of the spectrum, objects in deep space twinkle, and they twinkle because of the vast clouds of charged particles around our sun. And the smaller they are, for constant energy, the more they twinkle. So if you could spot a radio source that was scintillating a lot, then it was probably a quasar, a tiny but star-like object. So Hewish and his team, especially his research student, Jocelyn Bell, working here under Bragg's and then Neville Mott's patronage in the mid-1960s, began a survey of bright, twinkling radio sources. And in 1967, the summer of 1967, when most people in Cambridge were doing something completely different, though at least as celestial, Bell began to spot extraordinary phenomena, which were stars' radio sources that were producing pulses at amazingly regular, but amazingly short intervals of slightly under 2 seconds. So this is something that is immensely distant, but is producing something that reaches us with a period like that. And the first one that they spotted, the most obvious hypothesis was that this was a radio signal from intelligent source, what they called in those days an LGM, a little green man. So there was a brief, very brief period when perhaps this was going to be extraterrestrial life. But once Jocelyn Bell discovered another one in a completely different part of the sky with a very similar period, she realized that no LGMs could be involved, because it would be completely bizarre if two groups of extraterrestrials were both signaling on this rather strange frequency with exactly the same period, both directed at Earth. That seemed unlikely. And the culmination of the story, again, I think, emphasizes something that the whole story of Cavendish science brings out: the intimate relation between experiment and theory, without which these triumphs can't be achieved. There was then a very intense debate involving Hewish and Bell and Fred Hoyle at the Institute of Astronomy, probably one of the greatest theoretical cosmologists of the period, and Tommy Gold, who very quickly established that these must be neutron stars. These pulsars are what's left after a supernova. You have extraordinarily dense, hyper dense neutron stars, and as they spin, they emit radiation. And the period of the pulse shows you how tiny, how unbelievably tiny the neutron star must be, because it's producing a pulse once every just under 2 seconds from immensely far away. For pulsars, Hewish won the Nobel Prize. There's been a great debate about this. Should not Jocelyn Bell, who was the observer in question, have won the prize? Fred Hoyle, as was his wont, tough, pugnacious, genial Yorkshireman, said it was an outrage that Jocelyn Bell hadn't got the prize. That's become, as in the Rosalind Franklin case, an issue of debate ever since. So the story continues, but in terms of West Cambridge, that's really a different story. We would have to go to a different building. In 1975, the scientists moved out of these buildings to a glamorous new set of buildings in the western part of town, something much more industrial and factory-like than this congerie of Gothic, modern and postmodern architecture. And they were replaced by the social scientists, by the historians of science, the social anthropologists, the sociologists, people who work around Africa, and so on. The mercury under the floorboards had to be pumped out, the background radiation reduced, and history moved on. So what's the moral of the story? The moral of the story is that place matters. It seems to me that the intimacy of theoreticians, experimenters, students and technicians in what now looks to us to be extraordinarily crowded accommodation, with techniques and ideas being very rapidly circulated across disciplinary boundaries. I mean, this is a story that starts with electromagnetism and the ohm and telegraphy, and ends with pulsars and DNA from the 1870s to the 1960s, is a story in which disciplines are more often obstacles than resources. It's not a story of sealing wax and string. It's not a story of institutional poverty. It is a story of, I think, a kind of triumphant scientific geography.